So we're going to continue with chapter 7 stuff. Now, chapter 7 is all about electron orbitals, light waves and frequency, quantum numbers. So some of those words might bring you back to high school. I did some of this stuff in high school, so it might be a little bit familiar with you. So I have some stuff on electron orbitals, and then the de Broglie wavelength thing, and then some quantum numbers. Now, before we start, I want to mention this thing. Now, I posted this on the SI website, and I'm going to send the link to the SI website in the chat so you can access this. And we're going to be using this a lot this semester for the rest of the semester. So I see some of you guys are putting your emails in the chat. Thanks for that. And I just put in a link to the SI website. So if you click on that link, you can scroll down, and then there's a reference called the periodic table blocks. Now this periodic table blocks we're going to be using to determine the quantum numbers and the electron orbitals. So we'll get to this. We'll talk a little bit about this later, but if you can click on that link and then download the PDF yourself. This is also in the class notes. So,
is the electron orbitals the same thing as the configuration?
Yes. Yep.
Okay.
So like the box diagrams and stuff.
Yeah.
Yep. So before we start, are there any questions? Okay. Well, in that case, let's see, does anyone type a chat? No, just emails. Okay. So let's begin with discussing some electron jumping. So in numbers 1, 2, and 3, we're going to be talking about electrons changing from different orbital levels. So if I was going to draw a nucleus of an atom, and then you have the electrons that are orbiting around the outside. Now I know this is not a true representation of what the electron orbitals are like. They're much more complex, but let's just use this for our discussion just for now. Now you have electrons that are orbiting around the outside of the nucleus, and they can move up and down electron levels, and we represent the levels using n. So the first one, this is n equals 1, then we have n equals 2, n equals 3, and so on and so on. And so so your electron, if it's excited, could move up and move down levels depending on energy. Now, does anyone know what would cause an electron to jump up or down levels? I'll give you a hint. It's something to do with what we did yesterday. So if yesterday, remember we were talking about radiation and light waves. So if you had some electromagnetic radiation, which is the same thing as light waves, and it strikes an electron, then it's going to give its energy to the electron, and the electron is going to move up an energy level. So it might move up to n equals 2, or it might move up even higher. The important thing to note here is that the amount of energy that the electron gains is the same amount of energy of the photon. So remember yesterday we calculated the energy of the photons. That's how much energy the electron would get. Now, obviously moving up a level is going to mean you're gaining energy or you're absorbing. So moving up levels is absorbing, and moving down levels is emitting energy. So that should give you some insight into numbers 1 and 2. And for number 3, I have an equation that I want to tell you before I let you work on 1 through 3. And you can calculate the energy change for absorbing photons, and the equation is change in energy is equal to negative 2.178 times 10 to the minus 18 times 1 divided by the final n level squared, so n final squared, minus 1 divided by n initial squared. It's kind of a bad n here. So these n's are literally just the number, like n equals 1 or n equals 2 or whatever. So you have to put in the final n and the initial n and square those and then subtract them. Now there's another piece of information here that you're going to need before I let you work, and that is this term called ground state. Does anyone know what ground state means? Lowest energy level, yeah, Elizabeth. So Elizabeth said in the chat, lowest energy level. So this means n equals to 1. Very good. So using this information, you should be able to get through 1 through 3. But before I let you work, what questions do you have so far? Okay, so go ahead and try to take some time on your own for a few minutes and work through 1 through 3. All right, let's look at numbers 1 and 2. So starting with number 1, you have an electron moving from level 2 to 5. So does anyone have an opinion? Was a photon absorbed or emitted in that process?
Absorbed.
Yes, very good. I didn't see who said that. So yes, number 1 is absorbed. So it's going from levels 2 to 5, so it's going up, so it's absorbing. And conversely, number 2, so levels 2 to 1, it's going down, so a photon is going to be emitted in this process. Very good. So moving on to number 3. So first of all, was energy absorbed or emitted in this process? Well, once again, we're going from state 1 to state 4. So this is going to be an absorption. So 3 part B says calculate the energy transition for this process. So we're just going to plug in a change in energy is negative 2.178 times 10 to the minus 18. And in parentheses, we have 1 over the n final squared. So this would be 4 squared minus 1 over n initial squared, which is 1 squared. So from here, it's just going to be putting in your calculator. And so you would have, here you would have 1 divided by 16. And here you'd have 1 divided by 1. And when I did this, I got 2.042 times 10 to the minus 18 joules. If you have trouble doing that in your calculator, please let me know. Okay, so we got the first 2 parts done. The next part says, what is the wavelength and frequency of this photon? So keep in mind that when the energy change that's associated with this electron is going to be, it's going to be absorbed from a photon. And the photon's energy is the same as the amount that was absorbed. So let's see here. If we want to first find the frequency, you could find the wavelength first. I just did the frequency, but it doesn't matter. So using the equation from yesterday, so energy is Planck's constant times frequency. And so frequency would be energy divided by Planck's constant. So the energy change we found up above is 2.042 times 10 to the minus 18 joules. And the H value is 6.626 times 10 to the minus 34 joules times seconds. So if you weren't here yesterday, the H value for Planck's constant is always the same. It's always going to be 6.626 times 10 to the minus 34. So for here, we get that the frequency is 3.082 times 10 to the 15. Oops. And does anyone remember the units for frequency?
Is it? I forgot. Never mind.
Okay. So the unit is Hertz, HZ. I think it was, that was a guy's name, Hertz. You could also say 1 divided by seconds or seconds to the minus 1 power. They all mean the same. So now that we have the frequency, we can find the wavelength. Now there's 2 ways to find the wavelength. You can either use the C equals lambda V equation, or you can use energy is equal to HC divided by wavelength. Either way, I ended up using the C equals lambda V equation. And so this solving for wavelength would be C divided, or lambda, the wavelength, is C divided by frequency. So you're going to get the same answer either way. So the C value for speed of light is 3.00 times 10 to the 8th meters per second. And the frequency we solved above is 3.082 times 10 to the 15 hertz. And so I get the wavelength to be 9.8, no, I did not, 9.735 times 10 to the minus 8 meters. What questions do you have on anything so far on today's worksheet?
Can you go through how you put the first equation in your calculator?
Yes, this one right here, this delta E. So what I usually do, oops, let me move this down just a little bit. So what I usually do is just do it by little steps. So here we have minus 2.178 times 10 to the minus 18. And so this would be 1 divided by 4 squared, and 4 squared is 16. So are you following that far, Megan? Okay. And then it's 1 divided by 1 squared, which is 1. So then what I'll do is I'll keep this here, and I'll do 1 divided by 16, which is 0.08 something. I can't remember what 1 divided by 16. So minus 1 divided by 1 is 1. And then I'll plug it into my calculator. So I'll just kind of take it step by step. That's how I do it, at least. So does that help at all, Megan?
Yeah, thank you.
Okay. Are there any other questions on any of this? Okay, so let's move on to the next topic, which is, I just want to briefly cover, which is the de Broglie wavelength. I believe I'm saying that name right. So does anyone know the equation for de Broglie wavelength? So the equation we want to use here is the wavelength, which is lambda, is equal to Planck's constant divided by mass times velocity, which is u. So let's write these down. Now, the de Broglie wavelength we use, I guess I don't know exactly the theory behind this, but it's something along the lines of when you have a massive object of any mass that's traveling so fast, then it can start behaving more in a wave nature than just a particle. And you can calculate the wavelength based on its mass and velocity. So the wavelength here, lambda is wavelength. And this is meters. The h is Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. M, this is mass of the object. And then this is in kilograms, so just be careful here, not regular grams. And then the U is velocity. And this is meters per second. So whenever you're asked to do the de Broglie wavelength problems, they're pretty much just plug and chug. So why don't you take a minute and try to crank out number 5. There's no trick question with number 5. It's just kind of plug and chug. So why don't you take a minute to try to do that? All right, so if you're still working, that's fine. But this one isn't too complex, so I'll just run through it quick. So plug in H, so 6.626, well, 6.626 times 10 to the minus 34. The mass is 0.006 kilograms. And then let's see, U, the velocity is 331 meters per second. And so this comes out to something really small. Yeah, 3.34 times 10 to the minus 34 meters. So really, really tiny. What questions do you have on anything regarding the de Broglie wavelength? Okay. So the next topic I had today is quantum numbers. So not sure how far we'll get with this today, but I want to at least start on it. Let me get this moved out of the way. Move those down. Okay, so beginning with quantum numbers. Has anyone ever heard of quantum numbers, either from the notes or from high school, and wants to maybe share what the purpose of using quantum numbers is?
It's the best way they have to determine the location of electrons.
Very good, Elizabeth. Yes. So Elizabeth said it's a good way to determine, or I don't know, it might be the only way to determine where an electron is located. Yeah. So if I was going to write something, I would say to locate and identify electrons in an atom. So the thing with atoms is they have a bunch of electrons. They don't just have a few. You can get ones that have, 50 or something. And so you need a way to communicate with other people which electron you're talking about and which orbital it is. And so we use quantum numbers to do that. Now, quantum numbers are a set of 4 distinct numbers, and every electron has 4 numbers. And that's all you need to describe everything about the electron. Now, the 4 numbers are represented with the letters N, L, ML, and MS. So the N is the principal quantum number, the L is the angular, the ML is magnetic, and MS is the spin. Now there's a range of possible values for each of these. So the possible values for the N quantum number, this is just counting up positive whole numbers. So 1, 2, 3, 4, 5, and so on. So it's 1, 2, 3, 4, or it's one of those numbers, starting from 1 and going up. And the way we determine these, and this will make more sense when we do some examples. But when we start talking about like 1s or 2p, as we're going to do in a few minutes here, it's whatever this number is here. So if you had a 3D orbital, it's whatever the coefficient in front is. That's the N quantum number. So the L quantum number then is the possible values here are 0, 1, 2, and 3. So they don't go up any higher. They're only 0, 1, 2, and 3. Now, how do you determine the L quantum numbers? Well, this is depending on the type of block in the periodic table. So if it's in the S block, it's equal to 1. In the P block, no, excuse me, in the S block, it's equal to 0. Sorry about that. The P block, it's equal to 1. The D block is equal to 2. And the F block is equal to 3. Now, I think this is a good point to pause on the quantum numbers and go back to that reference sheet I was talking about earlier and discuss what am I meaning by S and P blocks and things like that. So I'm going to go over there really quick. Now, the periodic table is broken into 4 sections. Now, when you look at this, you see the purple section, that's the S block. The green is the P block. The yellow is the D block, and then the blue is the F. And each element is within a certain block. So when I say if the P block, if the element is in the P block, then the quantum number is 1. The way you determine that is by looking at the periodic table, finding the element, and just looking which block is it located in. So going back to here, if the electron or element you're looking for is in the S block, the L value equals 0, and so on. Okay, I know this is a lot. If you have questions as I'm going, please feel free to stop me.
For the principal,
Yep.
if it landed like in the configuration, if it ended with like a 3, so that would be your answer.
Yes,
Okay.
so like if it was in this 3p here, for example, then the principal would be 3. Is that what you're asking? Okay. Yeah, good question. All right. So continuing on, so the magnetic quantum number, this is one number within the range of negative L to positive L. So to get the magnetic, we need to know what the L value is first. And then it has to be somewhere between the range of negative L and positive L. Now, the way I determine this is by the room number, quote unquote room number, or the quote unquote box number. Now, I know this doesn't make much sense right now, but I promise this will start coming together when we do an example. And lastly, the spin quantum number, which is the last one, the possible values are either plus 1/2 or minus 1/2. And the way you determine these are if an up arrow is in the box, that equals positive 1/2. And a down arrow, this is going to equal negative 1/2. So it's the direction of the arrow in the box. Now, I know this is overwhelming and confusing. It was definitely for me so when I was learning this as well, but I promise it will start coming together when we do examples. But for so far, what questions can I answer for you on the quantum numbers?
So for the magnetic possible values,
Yep.
for, like you could have -2 and 2. Does that, like, is it, I don't know how to phrase this.
Yeah.
Could it be literally any like decimal value between -2 and 2?
Good
or
question,
is it
Elizabeth.
-2 or +2?
So here's what I mean by negative to positive. Let's say the L was equal to 2. So first we find the L value, and we found that it was equal to 2 here. That means that ML has to be one of the following: -2, -1, 0, +1, or +2. It's one of those numbers within the range of -2 to +2. Does that make sense, Elizabeth? Okay. Yeah, I know that's.
Sorry, go ahead.
Oh, I was just saying, I know that's confusing.
Will it always be whole numbers? Will it ever be a decimal? Do we have to worry about
Yes,
that?
it will always be whole numbers. Good question. Okay, so moving on to number 8. Lastly, before we get to doing some examples with quantum numbers, the basic shape for the following orbitals. So we have an s orbital, p orbital, d, and f orbitals, which correspond to the blocks on the periodic table. And so here's the basic shapes. So the dot I drew is a nucleus, and then an s is just a sphere. A p orbital is going to be like a sort of a figure 8 shape. Sometimes I call it a dumbbell. And these shapes are probability densities for where you might find the electron at any point in time. So these shapes show where it's most probable to find the electrons. For the D block, you have a figure 8 again around the nucleus, but it's in 2 directions. So it's like this. So that's where you're likely to find the electron. And then the F block, this one is too complex to draw, and you won't really be asked about it. If you're interested, you can go to Wikipedia, and they have some pretty good images. So before we do some example problems using the quantum numbers, what questions can I answer for you? Okay, so let's begin doing an example on number 9 with nitrogen for quantum numbers. Now, what I want you to do is, if you don't have this reference sheet, go ahead and take a photo of it right now, because we're going to be using this. And I'll be flipping back and forth. So the first thing we have to do, if we want to find the quantum numbers, is find where nitrogen is located on the periodic table. So we're going to find the quantum numbers here for nitrogen. And we're also going to fill out what's called the orbital box diagram, or electron configuration. So let's find nitrogen on the periodic table. And we find nitrogen is located right over here. So nitrogen is this one right here. Am I right on that? That's nitrogen, or is that oxygen? That's oxygen. Nitrogen is this one. So right here. Correct me if I'm wrong about that. So nitrogen is in the 2p box. Now, to get to the nitrogen, though, we can't just go directly to 2p. We have to first pass through the 1s. So we pass through the 1s, pass through the 1s here. Then we go down a row, we come to 2s, go through that, and then we come to the nitrogen in the 2p. So we go through 1s, 2s, 2p. So let's copy that down onto our electron box diagram, where this first line here represents the 1s box, this is the 2s box, and this is the 2p. Actually, there should be another line here like that. Now, each of the boxes is going to have 2 electrons. So once you get this copied down, I'll jump back to the periodic table quick. So we have our boxes 1s, 2s, and 2p. And I'm going to go to the regular periodic table here. So here's nitrogen. The next thing we have to do is get the number of electrons for nitrogen. Now, who can tell me, here's nitrogen, how many electrons does nitrogen have?
3.
Yeah, so yeah, it's 3 Ben in the 2p, but how many total does it have?
It'd be 7.
Yes, 7. Yep, not a trick. So right here, this number, this is the number of electrons it has. So let's write that down. We need, so nitrogen has 7 electrons. 7 electrons. Now we are going to take these 7 electrons and we are begin to fill out our box diagram with arrows, and every arrow represents 1 electron. Now just watch how we fill these. So we fill 1 arrow and then 2 arrows. So that's 2 electrons, 1 up and 1 down. Then we go to the 2s, so it's 3, 4 electrons. And then we do the 2p, so 4, 5, 6, 7. So we have 7 electrons that we just placed in our box. So now we have our orbital box diagram completed.
Why did
So-
the ones in the P all go up?
Good question. Does anyone know the answer to that? Why they all go up?
Don't you
Isn't
want
it
to
because you
complete
have
like
to
the
fill-
orbital? Yeah, you go ahead.
Oh, you just have to go, well, with the P's, you have to get, you can't just double up since there's 3 lines. You need to go across before you come back and do it again.
Yes, that's correct. That's exactly right, Megan. So you have to fill 1 electron in each box before you put 2 in one box. So you should go across and then come back. Yep. And there's a rule for that. I can't remember what it's called. So let's do the quantum numbers for nitrogen. Now, you always take the last electron that we placed to analyze. So we're analyzing this one right here. And we have 4 quantum numbers. We have N, L, ML, and MS. So the N quantum number, we said the N quantum number was the coefficient on the block. So we're in the 2p block, so N equals 2. For the L, we said the L was going to be equal to depending on what block you're in. So the P block, the L is always going to be equal to 1. And that was just right up here. So L is going to be equal to 1. The ML, again, so ML is a range based on negative L to positive L. So in this case, it would be -1, 0, and +1, where the -1, 0, and +1 represent the boxes that have arrows in them. Now, the last arrow is in the +1 category or the +1 box. Therefore, I'll do this another color. Therefore, the ML is going to be equal to +1. That's because the last arrow we drew was in the +1 box. Now, lastly, we have the MS. Now the MS, remember, if the arrow is pointing upwards, then it's a +1/2. And so the last arrow we drew was upwards, so +1/2. And these would be your quantum numbers for nitrogen. So
And why'd you say that it was +1/2?
Good question, Dylan. So the +1/2 comes from right here. So if your arrow, the last arrow you draw is facing upwards, it's +1/2. And if it's facing downwards, it's -1/2. Does that make sense, Dylan?
Yeah.
Okay. What other questions do you have before I let you do an example on your own? Okay, so why don't you take some time and try to do the quantum numbers for carbon, And I already have the box drawn out for you here. And if you want, or if you're up for a challenge and you finish carbon, try doing iron as well. And as you're working, I know this stuff is brand new for you and it's really confusing. So please feel free to ask any questions by using your mic or the chat.
My only question is why is there's 3 boxes in the on carbon?
Oh, right here.
Yeah.
So the number of boxes comes from the number of elements in the periodic table divided by 2. So look here, Ben.
Oh, okay. Yeah, they're always.
Yeah, it's always going to be the same. So to answer your question, Kristen, for iron, the last would be 3D. Yeah, it's the last electron you draw. Sometimes it's weird. Some professors will say the 4p comes after 3D. But as far as the box diagrams, I believe Dr. Weena always puts the 4p first, then the 3D, which is a little weird. So 3D is last, to answer your question.
So then in the 3D, like with the box number, would it be -2 to +2 instead of -1 to +1?
Yes, very good. Very good, Megan.
Okay.
So let's at least get carbon done. I'm not sure we can get to iron, but we can go over the answer. I can tell you the answer for iron, or we can go over it Monday as well. So to go, let's do carbon. So carbon is 6th on the periodic table, and that means we have 6 electrons. So let's fill these in. So we have 1, 2, 3, 4, 5, 6. And I forgot to do the box names. So this is the 1s box, 2s, and then 2p boxes. So I always like to number the boxes, and you start by a 0 in the middle, and then you do -1 to the left and +1 to the right. So this was the last electron we drew. So that's the one we're analyzing. So we have our N, our L, ML, and MS. So once again, for the N, that is the number on the coefficient here. So N equals 2. The L is going to be determined by the letter here. So P, for P, the L is always going to be equal to 1. So L equals 1. The ML, this is the quote unquote room number or box number. So because this is in the middle box or the 0 box, the ML is 0. And then lastly, for MS, the arrow is facing upwards. So since the last arrow is facing upwards, it's +1/2. So there is carbon. Now, for those of you who did iron, let me just write down the answers here for you. So N is going to be equal to 3, L is equal to 2, ML is equal to -2, and MS is equal to -1/2. I know it's 5 o'clock. If you got this one, good for you. That's like really impressive. But we'll go over iron and some other ones coming on Monday. So we'll stop there for today. I hope you guys learned a little bit, and I promise this won't be so confusing the more we do. I hope you guys have a good weekend. And if you have any questions on quantum numbers, feel free to hang out for a few minutes. See you guys later.
Thank you.
You're welcome.
Thanks, Matt. Love you.
Yeah, see you, Ben. Hey, Luke, by the way, I can't have a meeting right now. I have a call at 5. Is there a time we can meet, maybe tomorrow or next week or something?
Yeah, we can try to set out a time tomorrow. I do have to look around when I have to set out time for my senior design.
Okay.
Potentially 12:30.
Okay.
12:30 to 1. Also, another potentially good time would be 3:30 to 4.
3:30 to 4. Okay.
Friday. That's
Tomorrow?
late Friday. Yep.
Let's see. I don't know what. I know my mom's coming. Is there any time we could do beginning of next week, maybe, Luke?
Yeah. Yeah, I'm just trying to get through this week because I don't know what's quite up with next week yet.
Okay.
Monday I'm pretty free.
Okay.
What is your schedule look like?
Anytime before noon or like 2 to 4 time.
Sunday I have a grading party. I think.
And if you don't know your Monday or next week's schedule, we can maybe send an email.
Okay. I know
closer.
Tuesday I have an excellent time between 9:30 and 11.
Yeah. Yeah, that works for me. I think I have lab until 10. No, maybe I don't. Would 10 work? 10 or 10:30?
Yeah, 10 or
On Tuesday?
10:30. If you want to say 10:30 to be safe, that works.
Okay, that sounds good to me. I'll write that down.
Tuesday at 10:30.
All right, good deal. Thanks, Luke. We'll see you later.
Yeah. Good seeing you, man. We'll
Yep, you
check in
too.
Tuesday.
All right, have a good weekend.